Good evening, sir.
Hello everyone. Good evening. Good evening. My name is Amit. This is week 7 for GATE NPTEL Physics live sessions. I'm taking electronics part from the GATE syllabus. Till now we have completed some in the first class current source and voltage sources, then semiconductors, and then final three classes were about sessions were about op-amp. This week and the next 2 weeks, so in total 3 weeks, we'll be talking about digital electronics. And as always, if you have any questions, feel free to stop me. I'll start with some concepts with every question, then we'll solve some questions, and then I'll summarize the questions. And finally, at the very last, I'll again ask for some doubts. So feel free to stop me whenever you feel you have a doubt or I'm doing something wrong. Please correct me even then. All right, it's 7:02. We'll wait for 2 or 3 more minutes, waiting for people to join, and then we'll start the session for today. Till we wait for the people, if you have any doubts or comments, feel free to ask. Yeah. All right, let's begin. Welcome again. My name is Amit. This is week 7 for GATE NPTEL Physics live sessions. We have been talking about questions related to electronic session as far as GATE physics is concerned. And from today and for the next 2 weeks, we'll be talking about digital electronics. So 3 weeks of digital electronics. So let me just share my screen with you and let's get started. Is my screen visible?
Yes, sir.
Okay, good. And I'm audible also, loud and clear.
Yeah.
Okay, good. So let's begin. This is week 7, September 25, 2022. Excuse me for a second. All right. So, sorry again. Okay. So first we talk about what are number systems. So typically number systems is a system by which we count, and the way to count is through humans have devised a way we count through numbers. We call those entities numbers. Like to express a word, we use an entity called alphabets. So typically what the most natural thing that humans have evolved is a decimal number system where we use the symbols. Let me use my pen. We have evolved a decimal number system where we use the symbols 0 to 9, and mathematically what we mean is that we have a base 10. So we'll see this thing coming again and again, base. And the most characteristic feature of this number system is it's human. I mean, this is the most natural thing that comes to us. We are growing up, we see these numbers all around us. Our age is expressed in numbers, age 1, age 2, age 3. So right from our childhood we are exposed to these numbers. However, a computer, a machine that is, requires a much simpler nomenclature to express itself or to understand, to communicate with humans. So humans evolved another number system for machines, for computers in particular, which we refer to as binary. The number is explanatory. Binary means 2, hence the base 2, and the symbols which we use to express this number system, we just need two numbers, 0 and 1. Usually in binary number system, 0 is referred to as off state, 1 is referred to as on state. So you can either be off or on as far as a binary number system is concerned. And the most characteristic feature of this number system is its simplest. There are no if or but. Either you are on or you are off. There's nothing in between, ideally. So it's the simplest thing to understand, whether you are there or not, 0 or 1, on or off, simple. However, as how should I say this, as technology progressed, what computer scientists realized is that binary is taking too much of space. So let's say we'll come to this, but let's say you want to write decimal number 7. So we express decimal number as this, 7 to the base 10. We want to express this in binary. So we'll come to this, but just trust me that this number is 111. So 7 in decimal requires 3 spaces to store the same number. Another number is, let's say, 255 to the base 10. And when we convert it in the base 2, it takes 8 or 9 spaces. We'll see how many it takes, but it takes a lot of space. So in order to save this, so we compromised a bit. So we said we'll save a bit of space and we'll add a few extra symbols. So hexadecimal number system is base 16, and it uses the symbols 0 to 9 just like decimal, plus 6 other symbols. So 0 to 9 are 10 symbols, plus 6 other symbols are English alphabet capital A to English alphabet capital F. And why this was evolved? Because we want to express the same number which is taking too much space in binary. We just want to compress the data storing. That's it. There's nothing special about it, and we'll see that. Another number system which has been in use is the octal number system. As the name suggests, the base is 8 and the symbols used are 0 to 7. Its salient features, like somewhere in between, you can see it's a combination of compression and simplest. So it lies somewhere in between. So that's why I did not put anything. It's depend on your usage. Usually what you will see is that obviously decimal is the one which we are familiar with. So this will be our, how should I say this? This should be our go-to number system. Whenever we are in doubt, just go to decimal. You will be able to understand anything and everything. Binary, every computer works in this field. However, hexadecimal is a binary and hexadecimal. We use both of them. So let's see. I will not comment anything here which one is better, but we'll see. Right, that's all. That's all good. The problem is that how to convert one number system to another. That's why I told you. Let's say you want to express number 7, which is in decimal, so base 10, decimal number 7. How to express in binary, let's say. So it's a very simple thing. So first, let's say the number that's given to us is 7. So like we take LCM, I'll do the same. So if you want to express in binary, I'll write 2 here. So 2 3s are 6. Remainder is 1. We write remainder on the right hand side, and the quotient here again. The divisor is 2, so 2 1s are 2, and the remainder is 1 again. And if you do it again, divide by 2, there is no sense because it will come again 0. So, and we start writing from here to here. So our number becomes 1 1 and 1. Now let's do one more. Let's do 8. How does 8 look like? How does 8 in decimal number system looks like in binary number system? Again, I'll do the LCM thing. So 2 4s are 8, and so decimal, so remainder here is 0. Again 2 2s are 4, remainder here is 0, and 2 1s are 2, so remainder here is 0. Again we write from here to here, so the number will be number 8 in decimal base, in decimal number system will be 1 0 0 0 in binary space, in binary number system, sorry. So that's how we convert. Similarly, we can convert any other number. So let's say I want to write 24 in hexadecimal. In base 16, what does this number look like? Very simple. Divisor is 16 because the base is 16 here and the dividend is 24. So 16 ones are 16, that's the quotient here, and the remainder is 8. I told you right from here to here. So 24 in decimal number system will come out to be 18 in hexadecimal number system. So it will be different in every number system. So that's why we say 24 in decimal number system to the base 10 is 18 in hexadecimal number system, which is we denote by the number 16. Right. So this is how we do it. This is how we do it. So you are whenever you are given anything, just convert to decimal form and then convert it to the requisite number system using the LCM technique, which I demonstrated using 3 examples. Right. Another trick here. So let's say we want to convert binary to hexadecimal. So there's a very simple trick. Let's say the binary number here is, we are talking about 1110 in binary. What is this in hexadecimal? So it's very simple that these 4 blocks will correspond to exactly one symbol of hexadecimal. So every 4 blocks of binary corresponds to exactly one symbol of hexadecimal. So this will correspond here to, so how do we convert it? We convert it 1 into 2 ki power 1, 1 into 2 ki power 2, and 1 into 2 ki power 3. So 2 ki power 3, 1 into 2 ki power 3 plus 1 into 2 ki power 2 plus 1 into 2 ki power 1, that's 8 plus 4, it's 14. So this number will be 14 in decimal. Now in order to convert from 14 to decimal, this will be again in hexadecimal, this will be A, B, C, E, because 10 in decimal corresponds to A in hexadecimal. So similarly, so 10, 11, 12, 13, 14 in decimal will corresponds to E in hexadecimal. So you see, the 4 symbols of binary corresponds to exactly one symbol of hexadecimal. That's what I wrote here. 4 symbols of binary would mean one symbol of hexadecimal. Similarly, 3 symbols of binary will correspond to one symbol of octal. We'll see one more example here. Based on this, I have a question. So this question was asked in 2020 GATE physics exam. So the question is, which one of the following is correct binary equivalent? So we are given F6C in 16 is equal to what in binary? So there are 2 approaches of doing it. So approach 1 is convert hexadecimal to decimal and then convert decimal to binary. This is a long approach here. What we know, approach 2, since we know 4 symbol of binary are equivalent to one symbol of hexadecimal. So what I'll do is I look only at C first. So I look C in 16. I know C in 16 corresponds to, so A, B, C. So that's 12 in decimal. And I know 12 in decimal can be written as 1100. How do I get from this here to here? Again, you can do the LCM thing. So when you see 12, so 2 6 are 12, remainder is 0. 2 3s are 6, remainder is 0. 2 1s are 2, remainder is 1. So the number is right from here to here, 1100. Right. So C in hexadecimal is 12 in decimal, which is 1100 in binary. Now look at the other symbol, 6. So I'll write 6 in hexadecimal is 6 in decimal itself, which is again 0. 6 is 0110. Yeah, 0110 in decimal. How do I get this? You can do again this 6, 2 3s are 6, remainder is 0. 2 1s are 2, remainder is 1. So 110. 6 corresponds to 110. And again, remember that it has to be 4 symbols. So we have to add one extra 0. We have to add one extra 0 because it always has to be blocks of 4. Remember that. The final number is f. F in 16 corresponds to, we know that it corresponds to 15 in decimal, and you can again do the calculation. It will come out to be 1 1 1 and 1 in binary. I'll do 15. I'll do 15 because we are practicing. So 2. So 2 sevens are 14. Remainder is 1. 2 threes are 6. Remainder is 1. 2 ones are 2. Remainder is 1. Count from here to here. So that's why we get 1 1 1 1, which I have written here, 1 1 1 1. So what's the number now? The number originally was f. I'll use another pen. So the number was f6c. So I know c corresponds to, I calculated this, 1 1 0 0. I know 6 corresponds to 0 1 1 0. 0 1 1 0. I know f corresponds to 1 1 1 1. So what's the final number? This is the final number. So the final number is 1 1 1 1. 1 1, only one option has that, B. 1 1 1 1 0 1 1 0 1 1 0 0. So that's how we calculated, rather than going through this approach, which again correct answer, but this is a very lengthy approach because you have to okay, I'll do one more thing. I'll solve this using this also. F6c in 16 is what in decimal? I'll do this. So the way to do is multiply it by 16 to the power 0, this by 16 to the power 1, and this by 16 to the power 2. So this will come out to be 15 into 16 square plus 15 into 16 to the power 1 plus 6 into 16 to the power 1 plus c into 16 to the power 0. So that's 15 into 256 plus 96 plus c is 12. So what is 15 into 256? 256 into 15 is 3840. So my calculator says this is 3840 plus 96 plus 12. So this is 108. So this will be 3948. So the decimal number corresponding to this is 3948. Now you have to convert this decimal number into binary using this approach, the LCM approach, which again you will get, but that's a lengthy thing. So the shortcut here is that the thing to remember is that every symbol in hexadecimal corresponds to 4 symbols of binary. 4 symbols of binary. So for instance, 6 here in hexadecimal we calculated is 0110, not 110. Remember that this is not correct. There has to be 0110. So 0 has to be appended. Remember that. So that's about number systems. Now that all is fine. Now what we do is that what we do with numbers, like in mathematics we have some numbers from, let's say, decimal 0 to 9. We have these numbers 0 to 9. What we do is that with these numbers we do some operations, addition, subtraction, multiplication, division. Similarly, for the values 0 and 1, this we call them as Boolean, because our good fellow Boole formulated this algebra for us. So the values 0 and 1, the binary number 0 and 1, there are some operations that we can perform. One is conjunction. Conjunction is and. Disjunction. Disjunction is or. Negation typically we refer to as not. Right. So these are the values that we can play with. These are the 3 basic functions that we have, and these are the 2 very basic laws in Boolean algebra. These are called De Morgan's laws. So what it says is that there is one value, there is one element A. Again, remember that A can take either 0 or 1. A can have any of these values at any given point of time. Similarly, B can have 0 or 1. Not both of them together. Any one of them, or anyone. Like A can be 0, B can be 0, A can be 1, B can be 0, and so on. So what this law says is that A dot B, this dot symbol means and or conjunction, like I told you here, plus this symbol means or technically is referred to as disjunction. This symbol, the bar symbol that you are seeing, is called not or negation.
Hello sir, your voice is not clear.
Voice is not coming at all or very low? Since when did I drop off? Hello? Hello. Hello.
Hello, sir.
Am I audible now? Am I audible?
Yeah.
Yes.
Screen is not visible.
Yeah. So what is the last thing that you saw? I'm sorry.
Demorgan's law.
Okay. Okay. Good. I'll go to that. All right. Yeah. So De Morgan's laws. De Morgan gave two laws. So this is the first law. This is the second law. So what it says is that so A can take any of the value 0 or 1, and B also can take any of these two values 0 or 1. What De Morgan law says, first I'll identify the symbols. This dot that you see is referred to as and. This plus symbol that you see is called or symbol. This bar that you see is called not. Okay, so these three are the these are the primary operations. Conjunction also referred to as and, disjunction also referred to as or, and negation also referred to as not. So what De Morgan says is that when you multiply two values A and B, and you take, first you multiply, then you take the negation. So this is equivalent to saying that you take the value of A, its negation, and OR it with negation of B. This is the first De Morgan's law. A counterpart to this is the other thing. I'll repeat again. This dot means and. This plus means or, and this bar means not. So what it says is that the second law says that if you take an or of A and B and then take a negation of it, this is equivalent to saying that you have taken the negation of A and you have taken a negation of B. Sorry, this is not a bar here. And then you simply multiply them, you AND them. This is the second De Morgan's law. So like in every algebra we have some laws. So I'll say that. So 1 plus 1, we know in primary school mathematics this is 2. 2 plus 1 is 3, and so on. These are laws. These are addition laws in mathematics, primary school mathematics. Similarly, 1 into 2 is 2. 2 into 1 is also 2. Laws of multiplication in primary mathematics. Similarly, these two are the laws of Boolean algebra, which are called De Morgan's laws. We'll be using them very extensively. Very extensively. In fact, these two are the only laws based on just these two expressions. You can solve every question of digital electronics as far as logic gates are, digital electronics is concerned, logic is concerned. We'll see that. We'll come to that. But these two are the very basic laws, and you should be very clear in them. There should be no scope of confusion. Try to solve some problems with them. We'll see. We'll come to that. We'll come to that. Right. So this is all algebra. Okay. But in physical life, we also have these and, or, and not. So from paper, how do we go into real life? This is done through something called logic gates. This is something is done using something called logic gates. So from Boolean algebra on paper, which says that A dot B bar equal to A bar plus B bar, how do we do that? How do we take this negation? What is to be done? And how do we add the two signals? We don't know that. So the way to do is we use this something, a physical entity called logic gates. And every logic gate has a truth table associated to it. I'll tell you what we mean by truth table. So every logic gate performs a function. Let's first see that. So what this NOT gate performs is that you give it an input A. What it does is that if the input of A is 0, if the value of A is 0, the output will be 1. If the value is 1, the output is 0. So what it's doing, it's inverting it. Whatever the input is, the output is being inverted. It's being negated. Hence, this gate is called a NOT gate, and it's represented through this symbol, or mathematically, algebraic expression is this, and the symbol is this, a triangle followed by a small circle at the edge of the triangle. Right. This is called truth table, where we write every possible input combination possible. So A can have 0 or 1. and we try to find out the output. This entity is called truth table. Now, second important gate is AND, and expression is A times B. So this is how we express it. The inputs are A and B, output is X. So A can be 0, B can be 0, then A can be 1, B can be 0, B is 1, A is 0, and both are 1. So there are four sets of inputs possible, right? So what is the output? It says if A is 0, B is 0, output is 0. If B is 0, A is 1, output is 0. If B is 1, A is 0, output is 0. If both are 1, only then the output is 1. So what it's doing, it's like multiplying. So let's say multiply 0 by 0, answer is 0. Multiply 0 by 1, answer is 0. Multiply 1 by 0, answer is 0. Multiply 1 by 1, answer is 1. Hence the symbol is A dot B. A dot B, and hence this is called as AND gate or conjunction, right? Third important gate is OR gate. Again, come to a truth table. We just talked about that we can have these four combinations. So this is plus, remember this symbol, there's a plus in between. So let's say 0 plus 0 is 0, we know that. 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is not 2. See, this we are only talking about one input here. So actually in binary 1 plus 1 is 1 0. But as far as gates is concerned, 1 plus 1 is, this is high, this is high. So output will be high. So high is 1, not 2. So we'll see that in adders that carry happens, but here it's not the case here, right? Now there are other, see, these were the three primary functions I told you. This is negation or not. This is conjunction or AND. This is disjunction or. These three basic functionalities we talked about. Now we can combine these. How do we do? If we put an AND gate and consecutively, so just look at this. We do this and we do this. So what we are doing? First we are doing and then we are doing a NOT. This is called an AND gate, and the symbol is this. We put an and then we put a NOT gate. The truth table is this, so we know the output of AND is this, and then finally we are negating it simply. So let's negate 0, 1, negate 0, 1, negate 0, 1, negate 1 is 0. So the truth table for NAND gate is this. Similarly, how to form a NOR gate? Very simple. Put an OR gate and that simply invert its output. So what's an OR gate? OR gate is this. We have to what? We have to negate the output of OR gate. 0 inverted is 1, 1 is 0, 1 is 0, 1 is 0. So what we get is NOR gate. Two other gates are there which we encounter. This is called XOR gate, exclusive OR. Exclusive OR. Okay, the expression of this reads something like this: A bar B plus AB bar. A bar B plus AB bar. And this is the truth table for this. So you can just try to put this formula here and you'll get this truth table. Again, XNOR is nothing but you put an XOR gate and invert this. This is what XNOR stands for. This is the truth table for this. Again, I repeat myself, truth table is nothing. You put every possible combination of inputs and based on these inputs you find out the output. This is what is known as truth table. And these are some very basic logic gates which you will see repeating all the time. In these, NOT, AND, OR, NAND or NOR are most exclusively used. So that's this. Now, can someone tell me what is a universal gate?
AND gate.
Sorry?
No.
Sorry?
NAND gate.
No, I am asking what's the definition of universal gate. So let's say I ask you what is a human.
By which the combination of that can make any other gate.
Good. The word universal says that it's universal, means you can use this to formulate everything that's possible in the universe. Okay. So so what are these two gates? We have found out that NAND and NOR. I'll change my pen. Just 1 second. NAND and NOR are universal gates. Why? Because using NAND, I can do any of these operations. I can do NOT, I can do AND, I can obviously do NAND, I can do OR, NOR, XOR, XNOR. Everything I can do just by using NAND gates or a combination of NAND gates. We'll see in the next slide. So this was the question in 2020 physics. Which of the following is a universal logic gate? There are two universal logic gates, NAND and NOR. Why universal? We'll just see on the next slide, because you can form every other gate.
Hello, sir.
Yeah? Yes?
Your voice is not.
My voice or the screen or both?
Yeah, it's visual.
Okay.
And your voice also audible.
Okay. I think there's some problem in the connectivity today. I'll just keep on reminding me if my voice or screen goes off. Okay, just keep doing that. Yeah. So universal means you can form every other gate just by a combination. So NAND, I can let's say use 5 NAND gates to form I think XOR. We'll see in the next slide. Here is the slide. So this is the NAND symbol, right? What I am doing here is using NAND, I am creating AND gate. Simple. See here we are creating a NOT gate. So I'll try to prove this to you. Okay. So I'll try to make truth table for this. So input is A and output is, let's say, X. I'm saying this as X. Okay. So there are two inputs to an AND gate, 0 0 and 1 1. Only two inputs are possible because both the inputs are the same. So let's put 0 0 here. Let's check the value of NAND gate when we input 0 0. So when we input 0 0, NAND gate gives output as 1. Okay, I'll write here as, I'll change the color of my pen. I'll write here 1, right? So next let's see what happens when both the inputs to the NAND gate are 1. Okay, what happens when input is 1? So the output is 0. Okay, so what I'll do again here, I'll route output as 0. What's happening when the input is 0, output is 1? When the input is 1, output is 0. This is nothing but a NOT gate. So what I did is that just by using a NAND gate, I converted it into a NOT gate. Similarly, I can use this also. So if I do AB bar, this is NAND gate, and if I convert and if I use an inverter in front of it, it will convert it into an AND gate. So this is an exercise. I'm not going to do each and everything of this, but this is just an illustration that using just by NAND. So using NAND, I created an AND gate. So I use two NANDs here, NAND 1 and NAND 2, and the final output is an AND gate. Here for an OR gate, I use 3 NANDs, 1, 2 and 3. I created an OR gate. For an XOR, I used 1, 2, 3 and 4 and so on. So you can create every other gate just by using NAND gate. Similarly, just by using a NOR gate, we can create any other gate. So let's say again using NOR, using just one NOR, you have converted into a NOT gate. Similarly, using two NORs, you can get an OR gate, or using 3 NORs, you can get an AND gate, and so on. This is just an exercise. I advise you to just do a practice of these things. It's helpful sometimes because it's just Boolean algebra. Remember, it uses this 0 plus 0 is 0. Remember this, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. 0 multiplied by 0 is 0, 0 multiplied by 1 is 0, 1 multiplied by 0 is 0, and 1 multiplied by 1 is 1, and the two De Morgan's laws. AB bar equal to A bar plus B bar, and the second law is A plus B whole bar is equal to A bar times B bar. Just using these four and these two, you can solve every problem of logic gates algebra wise, right? So again, this question comes, the minimum number of NAND gates required to construct an OR gate is. So right, if you knew the theory, you could do this. Sometimes you might not remember the theory. So I'll now tell you how to solve these questions, that when we are required to find minimum number of NAND gates. How to solve these problems? We'll see that right now. So step 1 is write what is required to be found out. So we need to construct an OR gate. Okay, so I'll write y, output is y, OR gate is, we know it is this, a plus b. This is the OR gate. We discussed this here. Where is OR is a plus b. So what we need is that when we are given two inputs a and b, we want output as a plus b, right? Now step 2, you must always remember, you must always know that what is the expression for a NAND gate. NAND gate expression is AB bar. Okay, this is the expression. So what I need to do is that, see, this is a summation form, this is a multiplication form. So what I need to do, I need to convert this summation form to multiplication form. There is only one way to do it, that's De Morgan's law. So what I'll do is that I'll do this, y equal to y bar whole bar. Remember, I am doing nothing. Taking negation 2 times doesn't, so let's say if you take negation of 0, it's 1. If I take negation of 0 twice, so this is 1 negation, this is again 0. So when you take negation twice and not get twice, it doesn't impact the logic value. Okay, so let's do this. So let's put the value of y here. Y is a plus b bar whole bar. Okay, so now let's put a plus b. So we'll so what I'll do is that I'll apply the De Morgan's law here. Okay, so what I'll do here is I'll write it as, so a plus b whole bar is a bar times b bar whole bar. Okay, now compared to this formula of NAND, so the formula of NAND says that the first term should be multiplied by second term and whole bar. So let's assume that a bar is C and b bar is D. Let's assume this for a second. So what does this looks like? CD whole bar. This is nothing but NAND. See, this is nothing but NAND gate. So what I did, I created this. So if I input C here and if I input D here, what I'll get y. This is the expression, say y equal to CD whole bar. This is what I am doing, right? Now the value of C is a bar. Okay, so what I'll do is, the value of C is a bar. Now we know how to create a NOT gate from NAND gate. See this I told you this. So using a NAND gate we can create a NOT gate. So what you do, you short the inputs. Okay, so what I do, this. So what will this will give me? This will give me a bar, which is C here. Remember this is D. So D is b bar. So I can again get this b bar just from NAND gate. How? Just put the same, give the same input to both, give the same value to both the inputs. So this will be b bar. So this is how we create a NOT gate. We created an OR gate just from using NAND gates 1, 2 and 3. So let's see. So NOT and sorry, NAND. So 3 NAND gates we required. So the answer is 3. And I showed you this thing here also. So you see this OR gate. A was both the A was input to both the inputs for this NAND gate, and then same here, and then these were fed to another NAND gate to create an OR gate. So this is how we solved it. I'll repeat myself. Step 1, write the expression that what you want to find. So we want to construct an OR gate. So we wrote y is the output is equal to a plus b. Now we know that for NAND gate we require this form, some form of multiplication, but here it's addition. So the only way to convert from multiplication to addition is by using De Morgan's law. So what I did is that I write y equal to y double bar. Okay, and then I put the value of y here and I solved it. This came out to be a bar dot b bar whole bar. So I assumed a bar is C, b bar is D. So the expression came CD whole bar. This is nothing but NAND. So I created this. Very good. But C and D were not the inputs that were given in the question. So, but I know I can get C from A. How? Because I know C equal to a bar. And I know how to create a NOT gate from a NAND gate. So I did this. Similarly, I need to get D from B. How? Using a NOT gate. I know how to create a NAND gate, how to create a NOT gate, sorry, from a NAND gate. I use this. So this is the final circuit for an OR gate just by using NAND gates. So the correct answer here is 3. Right. So this is not a straightforward question. This, even if you know theory, you could solve it. However, when you were given this question, so in GATE 2022, the examiners knew that students are learning the theory. So they complicated the things. Now, again, what's the question? Find the minimum number of 2 input NAND gates. Okay. So we need to find the NAND gates. So circuit has to be in form of NAND gates, and we need to implement the following Boolean expression. So the expression is this. Okay. So we have to implement this expression using nothing but NAND gates. Okay. Now we know the formula for NAND is A, B whole bar. Remember this. So we have to convert this form somehow to a form similar to this. Multiplied and then whole bar. Let's do this. Let's solve this. So what I'll do, I'll multiply this inside. So A, B bar C plus A, B bar, BD plus A bar, B bar times C. Now, B and B bar, this term will be 0. Why will this be 0? Let's assume B value is 0. Let's assume B is 0. So when B is 0, this whole term comes out to be 0. When B is 1, this implies B bar is 0. Then again this whole term comes out to be 0. It's simply saying that 0 into 1 is also 0 and 1 into 0 is also 0. So both are 0. This term is never in the picture. So what we get is A B bar C plus A bar B bar C. Let's multiply C inside now. So I'll get A B bar C times C plus A bar B bar C. C times C is nothing but C. Remember that this is not your middle school or primary school algebra. C times C is nothing but C. High into high is high, low into low is low. Hence the terms like C square is C, C cube is also C, C to the power 4 is also C. Everything is like that. Plus A bar B bar C. Now take B bar C common. We'll get A plus A bar. Again, let's assume that the value of A and A bar. Let's create a truth table and let's find the value of A plus A bar. Okay. So A can be 0 or 1. Then A bar will be 1 and 0. Let's calculate the value of A plus A bar. 0 plus 1 and 1 plus 0. So this will come out to be 1. This will come out. So in every case, A plus A bar is always 1. So I can simply say B bar C times 1, which is nothing but B bar C. So this whole expression, I'll use another pen. Just wait a second. So this whole expression came out to be nothing but B bar C. So I get Y equal to B bar C. Now note that this is very similar to the expression here. These terms are getting multiplied, right? But what's not happening is that we are not getting this whole bar thing. So I'll do the same thing again. Very simple. This, right? So I'll negate it twice. Okay. So now I can simply say like this. So let's assume B bar equal to some symbol X. So I can simply say XC whole bar and then bar. Okay. So let me go to the next slide. Yeah. So we got Y equal to B bar C. I'll write it again. So we got Y equal to B bar C. So I'll write it again as Y is equal to double bar. So this is B bar C whole bar and then bar. This I can write as, so let's assume B bar equal to some other symbol X. So this will come out to be XC whole bar and then bar. Now note that this thing, the internal thing, this thing is nothing but your NAND gate, right? So I can create a NAND gate using this. So I'll see one input is X, the other input is C. So I get this internal thing, and then there is a bar on whole of this. So how do we create a NOT gate? We simply feed the same value to both the inputs. So what we get is, using this we have gotten now y is equal to nothing but b bar c. But note, we were not given x, we were given some b. So I can say x is equal to b bar. So how to, now in place of x, what I'll do, so this circuit remains the same, b bar c, y equal to b bar c. This was x, this was c. Now x is nothing but b bar. So we take, this is b. So this will come out to be b bar, because we know that in order to create a NOT gate from a NAND gate, we just feed the same value to both the inputs and it behaves as if it's a NOT gate. So this value comes out to be b bar. So this value comes out to be then b bar c bar, and then this b bar c double bar will come out to be y equal to b bar c. So that's how we convert. We can use what we can get using any Boolean expression, because NAND is a universal. Remember, this is a universal gate. So every expression, every Boolean expression can be expressed in terms of NAND gates. So what we did is that first we simplified this expression, we simplified it, and finally we got that the expression is this, y equal to b bar c. Now, but we need the form of this, something into something bar. So again I did the same trick, use double bar. So internal bar creates one NAND gate, and the external bar we can get this NOT gate using, we know how to create a NOT gate from a NAND gate just by feeding the same value to both the inputs, and that's how we solve this. So how many NAND gates are there? So we'll count this. So this is the first NAND gate, this is the second NAND gate, this is the third NAND gate. So the answer, the question asks the minimum number of NAND gates required. So the answer here would be 3. So 3 NAND gates were required to express this Boolean formula that we were given here, and this is the circuit that we used, right? Okay, finally, before ending the class, I like to go through one more question for a truth table. So remember, truth table is nothing, you list all the inputs and you try to find the output. Okay, so what we have here is, so on the left side to this thing is we have inputs, and here we have outputs. Okay, so the question says that find the value of x2 and y2. So we don't know these two, whether this is 0 or 1 or whatnot, we don't know. We'll try to find out these values. Okay, so let's do that. So I'll write this question again here. Let's solve it here. Okay, so what it says is that, so let's look at this line, second line, because we know the value of x and y in the first line. So let's look at this line. So I'll do the value of g is 0. I'll write here the value of g is 0, value of a is 0, value of a is 0, value of b is 0, value of b is 0, value of p is 1, value of p is 1, value of c is 0, value of c is 0, value of okay, so it needs, so this we need to find the value of this. This needs a value of y in the previous line. So value of y in previous line is 1. This guy requires the value of x from previous time. So the value of x previous time was 0, in previous line was 0. So this is 0. Okay, 0 into 0. So this is an AND gate. So the value of here would be, because 0 into 0 AND gate is nothing but, so this is AND gate. So this is nothing but a times g. The inputs are a and g. A is 0, g 0, output would be 0. This is OR gate. OR gate, this is c plus whatever this value, ag. So there are two inputs, 0 and 0. So output here will be 0 plus 0 is 0. The input here is 0. So 0 plus 1, this is an OR gate. So 0 plus 1, the value here would be 1. Okay, this is a NOR gate. This is a NOR gate. So what NOR gate does, we do the OR of them. So we'll do 0 plus 1 whole bar. 0 plus 1 is 1, 1 bar equal to 0. So the value of x will come out to be 0. Value of x2 here. So this is 0. Similarly, let's do this. 1 plus 0. 1 plus 0 whole bar. 1 plus 0 is 1 bar, which is 0. So the value of y2 will again come out to be 0 here. So that's how we do this problem. Very simple. Just put all the inputs that are given to you in the diagram. Very simple. And then just use the Boolean algebra laws. Which are the laws? I repeat, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. 0 into 0 is 0, 1 into 0 is 0, 0 into 1 is 0 and 1 into 1 is 1, and then if needed use De Morgan's laws. AB bar equal to A bar plus B bar, and A plus B whole bar equal to A bar times B bar. In this question the options we got was 0 and 0, so the correct answer would be B. Yeah, okay, so I am done from my side. It was a bit faster, it's okay. So if you have any doubts, you need me to repeat something, please ask. Any questions? Anyone? I'm audible, right?
Yes, sir. You are audible.
Okay, so was it too much? Too
No,
fast?
sir.
Huh?
No.
Okay. ठीक है. Any doubts that anything you want me to repeat, because sometimes these things can go fast, I know that. So for instance, some truth table sometimes it goes too fast, or minimum number of NAND gates. Any concept that you wish me to repeat, please tell me, or any concept that you from digital.
Last question.
Huh?
Last question.
Okay,
last question.
Okay, I'll do that. 1 second, let me share my screen. Screen is visible?
Yeah.
Okay, so what we were required to find the value of x2 and y2. This was the problem that was given to us. And so what typically you must always create an imaginary line here. See, x2 and y2 are the output. Why? Because they are on the right hand side. So these are called inputs and these are called outputs, right? So whenever what does this line suggest? This line says that when value of G is 1, A is 0, B is 1, P is 0, C is 0, you will get the output 0 and 1. This line says, third line says, when the value of G is 1, A is 0, B is 0, P is 0, C is 1, what you will get output as x, the value of x is 0 and the value of y will be output as 1. What we need to find is that what will be the value of x and y when these are the inputs. Okay, so I'll write these inputs here. Very simple. The value of G is 0, A is 0, B is 0, P is 1 and C is 0, right? But in order to find the value of x in line 2, which is x2 here, so I'll write x2 and y2. Remember that x2 needs an input, this input, right? This input is needed, but this is from a previous time, this is from the previous line, so this value is y1, because to calculate x2 you need y1. Similarly, to calculate y2 you need x1, because y2, whatever the value of x2 is being fed here to this logic gate. So in order to calculate the value of y2 you need x1. To calculate x2 you need y1, right? What is the value of y1? Y1 is 1. What is the value of x1? X1 is 0, right? So now now I know all the inputs. I know the value of every signal in this circuit, the value of every signal in this circuit. So 0 times 0, this is AND gate, so 0 times 0, the output will be 0. 0 times 0, output would be 0. 0 plus 0, this is an OR gate, so 0 plus 0, output would be 0. This is again an OR gate, 0 plus 1, output would be 1. This is a NOR gate. What does NOR gate do? It will do 1 plus 0, input here is 1, input here is 0, whole bar. 1 plus 0 bar is nothing but 1 bar, 1 bar is nothing but 0. So output here would be 0. Similarly, I'll do, this is a NOR gate, so I'll write this here. So inputs are 1 and 0 whole bar. So this will be 1 bar, which is 0. So the output would be 0. This is nothing but x2. x2 is 0 and y2 is 0. So I'll simply say x2 is 0 and y2 is also equal to 0 in this specific example. Is it clear now? Hello?
Hello, sir.
Yeah, what happened? How did the call get disconnected? When did the call get disconnected? Hello?
Hello.
Am I audible?
Yes, sir.
When did the call get disconnected?
When you explain input and output is imaginary line.
Okay, I don't know the. Okay, I'll do it again. It's fine. It's fine. There's no problem. I don't know how that happened, so I'll do it again. Screen is visible. I hope now, right?
Yes, sir.
Okay. So the left side is inputs, right side is outputs. Okay, that much is clear, right?
Yes, sir.
Okay. So what I do is that I need to find. So in the first line, what we know is that when we input the value of truth table means when the look at this row. So when the value of G is 1, A is 0, B is 1, P is 0, C is 0, you will get the outputs as these. Similarly, when you input G as 1, A as 0, B 0, P 0, C 1, you will get output as these. What we need to find is that what happens when you input the values G0, A0, B0, P1 and C0. So I do that. I'll do it again. Just hold on. Right. So I need to know what happens when these are input. So let's input these. A is 0, G is 0, B is 0, C is 1, sorry, C is 0, P is 1. I need to find what happens in this line. Okay. So we need to find the value of x2 and y2. Okay. So in order to find the value of x2, what we'll need to do is that, so let's calculate the output. 0 into 0, this will be 0. 0 into 0, this is an AND gate, this will be 0. This is an OR gate, 0 plus 1, this will be 1. 0 plus 0, this will be 0. Okay. Now we also need to find out the value here. This is nothing but y from a previous line. So this will be y1 here. Similarly, in order to calculate the value of y2 here, we need the value of x from the previous line. See, we are calculating the value of here, x and y here, but we need the value of x and y from previous line. So that's why, so the value of y1 here is 1. Remember, this is the value y1. This is y1. This is x1. So the value of x1 here is 0. So what we'll get here is, so 0 plus 1 whole bar, which is equal to 1 bar, which is equal to 0. So you'll get x2 equal to 0. Again here, this is a NOR gate. So the two inputs are 1 and 0. 1 plus 0 whole bar, which is nothing but 1 bar, which is equal to, so y2 you will always also get equal to 0. Hence the answer would be 0 and 0. Is it better now?
Yes, sir.
Yeah.
Sir, what if previous line values are not given? Would we have to assume them?
Okay, so usually in these kinds of problems, previous line values have to be given. If they are not given, you assume to be 0, 0.
Okay.
Usually they should be given, and if they are not given, assume them to be 0, 0, or the marks will be awarded to everyone. Okay. Okay.
These are, sir, flip-flops.
Yeah. So these are, This entity which you see on your right hand side, this thing is called a latch or flip-flop. We'll see this. I just wanted to bring it here to make you understand that truth table is just not for gates. Okay, that was my idea. We will see this. We'll see these latches and flip-flops sometime later. Okay.
Yes, sir.
Okay. Maybe in the third class we'll do that. So in 2 weeks from today. All right. We'll see them.
Thank you, sir.
Okay. Thank you. Sorry for the disruption in between. Yeah. See you next week.
Good night, sir.
Good night. Bye bye.